This is the key to the problems assigned for 6.2, torque and work. Make sure you've done these problems first before reviewing this key. Question 1. A wheel with rotational inertia I, radius r, initially spins with an angular speed of omega naught. A wooden block is pressed against the rim of the wheel as shown. The block exerts a normal force of magnitude F of n on the rim of the wheel, causing the wheel to slow down all the way to rest. The coefficient of kinetic friction between the wheel and the block is mu sub k. Which of the following is equal to the angular displacement of the wheel as it slows down to a rest? Now, here's a little test-taking tip for you. When you get these complicated looking formulas over here as answers, they're looking for a derivation. But sometimes, if you just think about it, you can probably pick out the right answer without having to go through too much trouble. What you need to know here is that the block is slowing down. And so the block is doing work on the wheel. And that work is equal to the change in kinetic energy. So work is torque times the change in angular displacement. All right. And so that work is going to be equal to this force here, which is coming from the coefficient of friction being applied. So anyway, the bottom line is that we have a formula on top that, if you remember, this is for kinetic energy, and it's got to have a square in it. So it's either got to be answer B or D. And then this one on the bottom, the difference between this denominator and this one is it includes the radius, which it has to do in order to apply torque. So the answer has got to be D. All right. Now I'll go through the formal derivation for you here, but I can tell you if I were taking this test, I'd circle D and I would move to the next question. So here we go. The block exerts a normal force on the wheel. That means it's being applied perpendicularly outside. The frictional force is the coefficient of friction times the normal force. That's a formula for the frictional force. So the magnitude of the torque, which is normally radius times the force times the angle at which is being applied, equals this force times the radius times the sine of 90, since it's perpendicular, and sine of 90 is 1. All right, so here's your torque formula. The magnitude of the energy dissipated by the torque comes from your work formula, which is torque times the change in the angular displacement. If you rearrange this for angular displacement, you get work over torque, and that's where this fraction is going to come from here, because this question is asking us about this angular displacement. So the magnitude of the energy dissipated by the torque is equal to the magnitude of the change of the rotational kinetic energy of the wheel. The wheel comes to rest, so the magnitude of the change of kinetic energy is equal to the initial kinetic energy, because the final is 0. So the change, you would subtract 0, and you'd be left just with this factor. So if we put this in as our numerator, because that's the amount of change of kinetic energy, which is equal to the work being done, and we put this in as our denominator, and we got to multiply it by 1/2 here, so the 2 goes into the denominator too, then this is the factor that you get. And so there you go. It was answer D. Question 2. The graph shows the net torque exerted on a rigid system that is free to rotate around a fixed axis as a function of angular displacement. 2 trials are performed. In trial A, which is here, a constant net torque is applied to the system. In trial B, a varying net torque is applied to the system as indicated by the graph. Which of the following correctly compares the work done in the system between trial A and trial B? Well, this is a torque versus delta theta, and that's our formula for work. In other words, what we want to calculate is the area under these lines and compare them. So the area of a rectangle for A would be 8 times 2 pi. The area of the triangle for B would be 1/2 times 16 times 2 pi. And if you do the math, both of those give you 16 pi. And so the answers are equal, so the answer should be B. In figures 1 and 2, a rod is initially rotating counterclockwise with an angular speed of omega naught about an axis at the center of the rod when the two tangential forces of magnitude F are exerted on the ends of the rod in directions indicated in the figures. I'm assuming this is at two different times. Frictional forces are negligible. The forces are exerted over the same angular displacement of the rod. Which of the following correctly compares work in figure 1 versus work in figure 2? The total work done on the rod, respectively. Well, if you take a quick look here, this force is being applied counterclockwise. This one is counterclockwise. It's spinning counterclockwise, okay? Here's the same force, but this one's going clockwise versus counterclockwise. If these two forces are equal, this thing will not rotate. If it doesn't rotate, then it has no work. Work equals 0. The only answer that has work equals 0 for figure 2 is answer C, and so answer C is the correct answer. There's no need to go through all the rest of those permutations and try to figure out whether or not you've made some kind of mistake. This is not rotating. There's no work. This is the only answer that shows that. This is the correct answer. Answer C. Question 4. In trial 1, a net torque with a constant magnitude, this is hard to read, but that is tau naught. So it's a little tau character with a subscript of 0. That's exerted on a disk over a time, delta t, bringing it from rest, so it's originally 0, to some angular velocity, omega 1. In trial 2, a torque with a constant magnitude of 2 tau naught, so it's twice as big, is exerted on the same disk, which again is initially at rest, for the same amount of time. What's the ratio of work in situation 2 versus situation 1? Well, work equals the tau times the change in angular displacement. All right, so if you double the tau, then the angular displacement is going to change. All right, but by how much is the question. So this takes a little bit of a derivation, and so here I'll show you how to do that. So work, like I said, is tau times the angular displacement, okay? You aren't given that, so you have to find a formula. Look on your AP equation sheet. This is the formula we have been going to right here. If this is 0, all right, and if this is 0, then this final angular position is equal to 1/2 the angular acceleration times the time squared. But we still don't know the angular acceleration either, so we can't stop here. We got to go back and find another equation, a very handy one, Newton's second law in rotational form. Here we could have alpha, and we could divide that moment of inertia into this torque, and we could substitute that for A right here. So alpha equals torque over moment of inertia times 1/2 times t squared. Now we have a formula for the theta. We can substitute that into our original work formula. Now we have work equals 1/2 tau over moment of inertia times tau times t squared. And tau times tau is going to be t squared. Now, why do we go through all that trouble? What we're trying to do is compare work in situation 2 to work situation 1. In situation 1, this is your answer. But in situation 2, this is 2 tau. And it's not just times 2, it's 2t, it's 2 tau squared. So you square this 2 and you're going to get 4. So situation 2 is going to be 4 times bigger. And the answer that shows a 4-to-1 ratio with W2 versus W1. You got to put them in the right order. 2 versus 1. The answer is A, 4-to-1 ratio. String is wrapped around a pulley of radius r as shown. Each end of the string is attached to a block, which are initially held at rest. The blocks are then released simultaneously. Block 2 of mass M2 begins accelerating downward. This one moves. Block 1 of mass M1 accelerates upwards. The string does not slip on the pulley. The pulley rotates with negligible friction. So it's telling us basically to ignore complications. The string exerts a tension force of magnitude T1 and T2. So even though these are T's, this represents a force, okay? After a time interval of some time, the pulley has an angular speed of omega. Which of the following expressions is equal to the pulley's rotational kinetic energy after time has passed? Well, kinetic energy is 1/2 the moment of inertia times the angular velocity squared. So we're going to need to find some of these values, all right? So this is one of those things that's going to take a little bit of a derivation. But again, if you take a quick look at the formulas here, you see all the similarities. This one shows it's going to be plus, this one's going to be minus. This has got to be the correct situation, okay? Because these two things are going to be fighting each other. One's going up and one's going down. So it's got to be either answer A or answer C. And it's not going to be answer A because that has a speed squared and a radius squared. So the answer is going to be C. But I'll go through the derivation with you just so you can see that that's correct. Here we go. Again, I know maybe you don't understand what I'm saying whenever I give you the answer, but I'm trying to tell you folks how to save time. You can figure out answers to multiple choice questions because the answer is in front of you. And your job is to find the right answer. It's not to prove it. I'm proving it to you here on the key. But your job is just to find it. And if you find it, circle it and go to the next question and quit worrying about it. But if you want an explanation, here we go. The formula that relates work and torque and angular position is the one we've been looking at all along in this unit. We aren't given theta, so let's go to our go-to theta formula. Again, fortunately, this is going to be 0 because it was at rest. This is going to be 0 because it was at rest. So our final angular change is going to be 1/2 the angular acceleration times time squared. Now, again, we don't know alpha. Last time I went to Newton's second law, but in this case, I don't need all the moments of inertia. So instead, I'm going to go to what alpha really means, which is the change in the angular velocity over time. All right. So if I substitute this in for A right here, I'm going to end up with time squared on top. This really is just a t on bottom, even though it says delta t. So that's going to cancel out. So that's going to leave me a t on top, the omega, and then times 1/2. Now what I just found was theta. What I need to find also is torque, okay? So let's go back and look for that. So I can put theta into that formula, but I'm still not done because I got to look at the torque. But torque is a net torque here. There's two torques at work. Torque applied here and torque applied here. And we got to designate one of them as negative. All right, so since this one's actually pulling it, let's call that one the positive. And since this one's going up, let's call that one negative. Don't pay attention to the direction because they're both pulling in the same direction, pulling the same direction. But because this one is winning the battle, I'm going to call it positive. So my torque really is the force times the radial distance that's being applied at. So really the string right here is R times this force. That's torque number 2. R times this force, that's torque number 1. So I'm going to subtract torque number 1 from number 2. plug that into my formula, make sure I multiply by R. Really complicated algebra, but it basically boils down to this. If I subtract the two torques, I get R times omega times delta T, and that looks exactly like answer C. Question 6, a net force of F1 is exerted tangentially to the outside of a uniform disk of rotational inertia I1 over an angular displacement of change in theta 1, causing the disk to gain rotational energy, delta K1. Now, the same net force is then exerted tangentially to the outside of a second uniform disk over the same angular displacement, causing the second disk to gain rotational energy. But the second disk has the same radius, but its rotational inertia is double. So which of the following is equal to the correct ratio? In this case, the ratio is 1 versus 2, so make sure you get those in the right order. What you're going to need in this case is the understanding that the change in kinetic energy is work, and work is torque times the angular displacement. The angular displacement stayed the same, the torque is the same, and so the kinetic energy change is the same. You're given a lot of information like this, the moment of inertia is double and so forth, that you really don't need to answer this question. So the answer was B, sorry. All right. Disk A and B are initially at rest. Strings with negligible mass are wrapped around the edges of each disk. Strings are pulled with equal forces of magnitude F as shown, so these two forces are equal. The disks are free to rotate about their centers with negligible friction. Disk A has a radius of R naught, rotational inertia I naught. Disk B has a radius of 2 times R naught and a rotational inertia that's 4 times larger. Which expression correctly relates the change in rotational kinetic energy of the two disks after each string has been pulled the same linear distance? So just looking at this now, they're pulled the same linear distance. That suggests to me the kinetic energy is going to be equal, which we answered B. But let's take a look at that. So the change in kinetic energy is going to equal your work. Work is going to be tau times the change in angular displacement, which we're not given. We're going to have to figure that out. And we can figure it out from this x value because angular displacement is going to be related to the linear distance that string is pulled. So this is going to require a little bit of derivation. Let me go ahead and pop the answer up here for you. So rotational kinetic energy gained is equal to the work done, as I said. That's going to be tau delta theta. Torque is the product of the radius and the perpendicular force component. Now the forces are the same, but the radius is doubled. All right, so let's keep that in mind. That's going to double that for situation number 2. The angular displacement defines the distance the outside moves compared to the radius. So here's a key. So you got to understand this, that the angle that this is making when it spins is related to how much string is being pulled right here. All right, the same amount of string is pulled, but this one's going to go half as far. All right, so those two factors are going to cancel each other out. So if you do the formula, work equals tau, which is the R times F, times the distance the string is pulled divided by the radius. But if you double this on top and you double this on bottom, those are going to cancel out and you're going to get the same ratio. And since you get the same work for disk 2 versus disk 1, that's the same change in kinetic energy for both disks. So again, what I did was I found the formula for this, the basic formula, RF. Basic formula for this, change in linear distance divided by the radius. I just doubled this and, oops, I went to the next one. I doubled both of them and they cancel each other out. Sorry about that. I can't go backwards on my laptop, so we're going to go on to number 8. Wheels A, B, and C have different rotational inertias. In an experiment, each wheel is spinning on its axis with a non-zero angular speed when a torque is exerted on the wheel as the wheel moves through an angular displacement, causing the angular speed to change by some amount. The table shows the values of torque, angular displacement, and change in angular velocity for each wheel. Which of the following correctly relates work in the three cases for the three wheels, respectively? Now, this is one of those cases where you got to be careful. They're probably giving you too much information, because if you just calculate work, all we need are these two values. All right, we don't need this. And so if you take a quick look at this, this has a 1, a 3, and a 2. This has got a 1/2 and a 2. So that's going to be 3. This is going to be 3 over 2, and this is going to be 3 over 2. So A and C are going to be equal to each other. The only choice that has A and C equal to each other is B. So the answer is going to be B. How you like that? I was right. The work done is defined as tau delta theta. Just multiply like I just did. 1 times 3 pi over 2, 3 pi, 3 pi over 2. A and C are equal, so the answer is B. And the last question. The net torque exerted on a rigid system as a function of a system's angular position, represented in this graph. Which of the following expressions is equal to the work done on the system? Now, in these questions, this is a torque versus angular position, so a theta. So those two multiply by each other gives us work. You've got to look for your zero line on your x-axis. So here's 0. That means we have to, if you multiply these two, you'll get the work. That means we need the area under the curve, but we need all of this, not just this up here. We got to count all these squares right here. So this rectangle is going to be 2 tau theta. This triangle is going to be 3 times 1/2, base times 1/2 base height. So it's going to be 3 over 2 times theta. So 3 over 2 plus 2 is going to give us 3.5. Now, I don't see a 3.5 on there, and my answer got covered up, but the answer is C, because that answer says 7 over 2, which is 3.5. So this was 3.5 is the answer that I got when I did the area, but the formula shown says 7 over 2. All right, so like I said, I can't go backwards on my laptop because of a stupid function. Maybe I could do that. Now I can go back. There it is right there. So 7/2, that equals 3.5, is the area under the curve. All right, so there you go. That's the answer. You know, it's a good idea, now that you've gone through the key, to go through these problems again on your own and see if you can remember what I told you. So good luck.